Working? Can you hear me? Okay. So I'm an industrial engineer like all of you here. The project that I'm about to present is actually a case that I worked on in Germany. Let's see the topic. Definition and standardization of attributive testing for the production lines of HVAC modules at Mahle. Complicated, so let's break it down together slide by slide. Okay. What does this project, or what did this project aim to accomplish? The project was studied and implemented in Mahle in Stuttgart. The main focus was the HVAC production lines, and the project was done on the span of 6 months in order to standardize an MSA methodology for the company. Let's go a little bit into details, but first, here's a brief about the company. Mahle is one of the main automotive suppliers that are found in Germany. It was founded in 1920. The products of Mahle actually range from engine systems, filtrations, electrics, mechatronics, and thermal management. Mahle is a daughter company of Mahle that was established only in 2013. It was established after Mahle acquired almost all shares of Beer, and ever since Mahle has been leading globally as a system supplier for vehicle air conditioning and engine cooling. And this is where my project was implemented. Before we dig deeper into the presentation, let's get a briefing to refresh your memory. What is MSA and what is gauge R&R? MSA, Measurement System Analysis. It is a mathematical experimental method used in quality control in order to measure the variations we have in the system. So when you want to measure quality, not only do you measure the quality of your product, but you want to make sure that your quality testing devices are in good conditions. We want to know that they are capable. And this is what MSA aims to do. It measures the variation found in the operation, in the measurement systems, in the interactions, so basically variation in general in order to reach a best practice quality. One of the main methods falling under the umbrella of MSA is gauge R&R. It stands for repeatability and reproducibility. Always difficult to say. Repeatability is the variation created by the system. Reproducibility is created by the variation of the appraisers, and gauge R&R also aims to measure the system's ability to detect those variations. We all know that we have continuous devices and we have attribute devices. Continuous devices are those that measure pressure and so on. Attributes, it's simple, wrong, right, black, wrong. To measure the capability of continuous devices, we simply use gauge R&R that is implemented through ANOVA, analysis of variances. However, when it comes to attributes, we don't really have a standard global methodology in order to measure those variations. So each company defines its own methodology in order to measure the variation in the attribute systems. And that is what this project did. Okay. So the objectives were to create this MSA methodology for the attribute devices in order to measure the variations and hopefully reach a zero defect rate. But as I said before, this project was done in the span of 6 months. It was divided into 2 phases. The first phase was the research and the desk work. The second phase was the actual implementation on the floors of the factory. So the first phase was we had to study different control plans. Mahle has a various customer portfolio, so they were all studied. Then we chose attribute systems to be considered for the study, and then they were categorized in order to study them in an efficient way. And then, like we can say, an initial test design was made. That was our first phase. Second phase was go to the ground, do trials until we reach a clear standard, and then define the methodology. But that was not it. We also had to define the frequency of how often should we measure the variation of our attribute devices. Okay, now let's dig a little bit deeper into each thing. So I mentioned before that we had to design a test. What did this test include? We had 7 components in the test design, which included, we have a reference sample, which was one that doesn't have any defects, which acted as our benchmark for our sample. We had to define a sample size, we had to find number of operators, number of trials to be done, but the most important one that I want to focus on is the percentage of defectives and design of defectives. Because in order to measure the variation, you need to trigger that device that you are studying in order to see how capable it is of not doing wrong. So by this design, you're triggering the weak points. So that was our main focus. And of course, we had the test frequency and the test conditions. I mentioned before that we categorize our measurement systems. So we divided them into 4 categories: visual, sensors, scanners, and cameras. Each category had almost 6 to 7 devices found within it, and those devices gave a holistic overview of all the devices found in the production line. For example, in the sensors, we had light sensors, laser sensors, ultrasonic sensors, and we made sure that they are found all around the production line in order to give one methodology that is applicable to all of them. Now, what statistics did we use? We talked about the design, we talked about the test components. Now, what did we test statistically as engineers? So we wanted to keep it simple, yet we wanted a thorough outcome. So we took into consideration alpha, beta, and the effectiveness. Alpha error are when you have a good part, but it's detected as a bad part. When you have a high percentage of alpha error, this means there's a problem with the miscalibration. Beta is a very critical value because it's a bad part, but it's actually defined as a good one. Here you have to say, okay, stop, something is actually wrong with my device. And then the effectiveness is like how effective in a percentage is my device. Globally, in statistics, 80% is our effectiveness rate that is accepted, and the same rate was used for this study. Down here, down here, we have a figure that shows the statistics that we had. For example, effectiveness in this test was 66%, alarming. Alpha error, which is the miss rate, was actually good. There was no alpha error. But for the beta error, it was a 50% miss rate. So that showed that something was highly wrong with the device. Okay, so we talked about phase 1 completely, how we dug into the categories, the design, and so on. Now phase 2, the application, how was that done? Basically, we implemented the first run without controlling the conditions and using our initial test design. After we took our results, we started manipulating the conditions. For example, we knew the camera was affected by the light, so we controlled the lighting around it. We knew that the sensors were affected by sound waves, so we controlled the sound around it in order to manipulate and see what really triggered that device. And then we fixated the conditions. We started manipulating the design of defectives. We fixated that, and then we started manipulating the sample size. I guess you can see the pattern. Basically, it's fixing everything and manipulating another in order to reach the weak point. After the trials were done on the ground, everything was plugged into a software called CUDAS. CUDAS is a German software that is used in the manufacturing industry all around Germany. So I had to take a training in CUDAS, and it was my main go-to point for my statistics. After that, it was very, very long 4 months of trial and error. A methodology was created and a manual was created. I'm going to run you very quickly for an example. We have this camera right here. This camera is supposed to detect if we have the right filter inserted in our HVAC. How is that done? It's actually very simple. You have the black bar right here. It takes a picture, makes sure that the length and the width are the same as the ones defined in its software. If yes, tick, check, it goes on. If not, then it should say stop, something is wrong. The camera is only sensitive to grayscale, so it doesn't matter if you use color. So basically the manipulation was done manually right here. We changed the length, the width, tried to add some black and white into it and see what's going on. The camera was actually proven to be in a very rusty situation because as you can see, we have a 62.5% miss rate, beta error. It's not a miscalibration rate, so this was a high indicator that, okay, the camera needs to be changed. But actually what was wrong was the conditions. Everything was fixed when we increased the lighting around the camera, then the miss rate was reduced to 0%. This right here took 6 weeks of trial and error, to be honest. So to wrap it up, each category had a different conclusion, a different range for a sample size, a different design of defectives, a different percentage of defectives. However, one conclusion stood out which proved to be right for all categories, which is the sample size. As engineers, we know in probability, the bigger the sample size, the better. However, that was proved wrong for attribute testing devices because actually here you don't really have a lot of probabilities. So when you reach a sample size of 40 and you keep increasing it up until 120, for example, you get the same exact result. So sample size was not the critical factor here, it was actually the design of defectives, which was better for us because it cut cost. So in my methodology, I defined in the manual that the sample size should not exceed 50 because you're just going to be wasting time running your trials. And we tried it all the way from sample size of 20 until 120 for each device, and then we just reach a plateau where there's no change going on. The standards defined took into consideration cost factors, time factors, and the availability of parts. You can't just go around doing an MSA test because basically you're going to have some parts that are going to be thrown away after the tests. The methodologies defined are simple, and they don't only give an indication of the capability, they also give an indication of the calibration of the device. The standards are not fixed. Attribute systems remain a gray area in the statistics of quality control. They could be subjective from one engineer to another. However, we took the ideal case, but they could be changed whenever seen necessary. So what was handed out at the end of this research were 3 outcomes. 1, a reference manual showing each category with a test design and a clarification of why this standard was given. And then it crossed my mind, what if a new device is to be introduced, but it doesn't belong to any of those 4 categories? So a more thorough research was done, and 9 guidelines were defined that the company can use in order to design a test from scratch for that attribute design. And then I actually prepared a manual on how to use CUDAs, since the statistics of the attributes was actually a new update for the software. And currently those manuals are actually found in Malibir. They've been under implementation for the past 2 years. And yeah, I can say this is the biggest accomplishment so far I have done. Thank you so much.